Learning Outcome 2-3, Sifting Theorem. This uses the fact that the impulse function is the convolution identity operator. Because the impulse function is the identity function for the operation of convolution, first we need to make sure you understand what an identity operator is. So let's consider addition. For addition, the identity operator is 0, because 3 plus 0 is 3. Addition of 0 does not change the value. The identity operator for multiplication is 1. 3 times 1 is 3. Multiplication by 1 does not change its value. The identity operator for convolution is the unit impulse function. Because if we take a function and convolve it by unit impulse, we get that exact same function back, whether we're in discrete time or in continuous time. So let's take a look at how convolution works if we were to do convolution with a unit impulse function. This is the Johns Hopkins University Joya convolution applet for discrete time because it's not possible to make a true impulse in continuous time. But here we have an impulse, and we're going to convolve it against another function. So let's see what happens. As we pass it by, look at what happens in this window to the product. We now have 1 times the amplitude of our function down here, which means when we add across there, we've got 0 everywhere else in just that 1 amplitude. If we move it over 1 further, we now just get the amplitude at this time, and adding it up, we get just that same value that shows up as our function. Going 1 further, again, we isolate just that 1 point in time, and that 1 point in time shows up as our output. So whatever we put in here for a function, if I were to change values, as we work our way through the convolution, in this window we are isolating only 1 point at a time, and that 1 point becomes the sole value of our output. The sifting theorem is built on this identity operator idea. These 2 lines show that convolution with an impulse gives us that same function out. The sifting theorem incorporates time invariance. The idea that if we shift something, we're going to shift something else. So if we take our function f of n and we convolve it with an impulse at a time n naught, we're going to get that same function out, but shifted to the time n naught. Similarly, for continuous time, if we take our f of t, convolve with an impulse at time t naught, we're going to get the same original function out at that new time t naught, at the time t naught specified by the impulse. Let's try some problems. Here's an x of n, convolve it with this impulse. This impulse is located at time 1, which is 1 unit further in the future. Therefore, what's the output going to be? It's going to be x of n at time n minus 1. Therefore, everything here gets shifted 1 unit in the future. Another example, x of n convolve delta of n plus 1. According to sifting theorem, our n naught is negative 1. So we're going to wind up with x of n minus or minus 1, or x of n plus 1, which takes our function here and shifts it 1 unit to the left. 1 unit to the left. Linearity properties still hold because convolution is linear. So we can apply both scalability. So here's an example. If we were to convolve with 2 times that delta of n plus 1, we're then going to get 2 times our x shifted to that location. And the additivity part of linearity also holds. So if we have 2 impulses, we have x of n convolve delta of n plus delta of n minus 3, so we can distribute and just convolve delta of n with x and delta of n minus 3 with x, giving us x of n and x of n minus 3. It works also with continuous time function. Here I've drawn a continuous time impulse. Notice it's an arrow instead of a dot, because this is a delta of t minus 1. T naught is 1. We're going to have f of t minus 1, which will take this and shift it 1 unit to the right. 1 unit to the right. Here's another example. This is now an impulse shifted 1 unit to the left, which will shift our function 1 unit to the left. Scalability also applies. This 2, remember, is area, not amplitude. And even though the amplitude still is just infinity, because it's 2 times infinity is still infinity, we tend to draw our impulses taller when they have a larger area, just because it makes us feel good. It's not necessary to do so. And x of t can involve 2 times delta of t plus 1 will be 2 x of t plus 1. Here, the change in amplitude is necessary. Addition also applies. Just distribute x of t to both terms. Earlier, when we introduced the impulse function, I introduced the no-name theorem. The no-name theorem is when we take a function and multiply it by an impulse. That's going to return, and we still have the impulse here, but it now only has one amplitude value or area value, depending whether we're in discrete or continuous time. No-name theorem is different than the sifting theorem. In the sifting theorem, when we're convolving, the impulse goes away at the end. You need both of these functions on your note sheet, but you need to keep them in your mind separate and make sure you can apply both of them to any problem where they're needed.